Hello, this is Dr. Hanaa Assil. This is Unit 3 of October 2023 in the Pearson International A-Level of the GCSE. So let's take a look at the questions and discuss the answers. So the first question here was, a student is given 3 solid compounds, A, B, and C. Each solid contains 1 cation and 1 anion. 2 of the cations are known to be sodium and potassium. The student carried out flame tests on separate samples of each solid to identify the cation. Describe the method for carrying out a flame test. How do we do a flame test? Remember, in order to do a flame test, we need a platinum wire. The first thing we do is clean a platinum wire by dipping it in concentrated hydrochloric acid. Dip the wire in the salt. Expose the wire to the non-luminous flame of the Bunsen burner. Remember, we said the non-luminous flame of the Bunsen burner, that is the hot flame of the Bunsen burner. Observe the emitted light. So this is how we do a flame test. Then complete the table of results. So what is the color if we have sodium ions? Remember, you're required to know these colors. If it's red, it's lithium. If it's yellow, it is sodium. So sodium would give a yellow color. Now what about potassium? Potassium ions would give lilac. Calcium gives brick red, strontium gives red. What if I have pale green? Pale green means there is barium ions. The student prepared separate solutions of A, B, and C using distilled water and then added dilute nitric acid followed by aqueous silver nitrate to each solution. A precipitate formed in all 3 mixtures. Identify by name or formula the 3 ions that could be present. Silver nitrate with dilute nitric acid is a test for what? Remember, dilute nitric acid with aqueous silver nitrate is a test for chloride, bromide, iodide. So if I have a precipitate, then this means that I have one of these halides. Compounds A, B, and C each contain a different anion. Describe the chemical tests on the precipitates that could be used to confirm which anion was present. Give the results of each test. Remember, if I add dilute nitric acid and silver nitrate, if it is white, it's chloride. If it's cream precipitate, it's bromide. If it is yellow precipitate, it is iodide. But the problem is, these colors are very close to each other. So actually, in practical lab tests, it's difficult to determine was this white or cream or yellow. And we said after adding dilute nitric acid and silver nitrate and getting these precipitates, we should test the precipitate to confirm which anion it is. How do we test the precipitates? We add first dilute aqueous ammonia. So we're going to add dilute aqueous ammonia to each of the precipitate. If a precipitate dissolves, that indicates that it was chloride. So the precipitate from chloride, when I add nitric acid and silver nitrate, it should give white precipitate soluble in dilute aqueous ammonia. What if it doesn't dissolve? If it doesn't dissolve, that means it's either bromide or iodide. So we add concentrated aqueous ammonia. The precipitate, if it dissolves, that indicates that it is bromide. If the precipitate does not dissolve at all in dilute or concentrated ammonia, then it is due to iodide. Question 2 says the molar volume of carbon dioxide may be determined using the reaction between calcium carbonate and ethanoic acid. So this is the equation for the reaction. Place 30 centimeter cubed of 1 mole per decimeter cubed ethanoic acid in a boiling tube. Set up an apparatus to collect the carbon dioxide produced over water in a measuring cylinder. So you should know that this apparatus should look like this. If I have my reaction in a boiling tube and then I want to collect the gas given off over water in a measuring cylinder, then we should have a delivery tube going into this big beaker, which is called the trough, and we have an inverted measuring cylinder. At the beginning, the measuring cylinder is full of water, but then as the gas comes out, it collects. So, after setting up this setup, he says place approximately 0.1 gram of calcium carbonate powder in a clean, dry weighing tube. Weigh the weighing bottle and its contents accurately. Remove the bung from the boiling tube, tip the calcium carbonate into the boiling tube, quickly replace the bung and collect the gas. When the reaction is finished, measure the volume of gas collected in the measuring cylinder, reweigh the weighing bottle, repeat the experiment 5 more times, increasing the mass of calcium carbonate by about 0.05 grams. Do not exceed 0.4 grams of calcium carbonate. So he's going to repeat it for different masses. And the first question is, draw a diagram of the apparatus used to carry out the reaction and collect the carbon dioxide produced over water in 100 centimeter cubed measuring cylinder. So he's basically asking us to draw the apparatus. So we said this is the apparatus that we should have. We should have a boiling tube, delivery tube, measuring cylinder inverted over water in a trough. Explain why ethanoic acid is used and not hydrochloric acid. Now, what's the difference between ethanoic and hydrochloric? You should know that ethanoic is a weaker gas. So, if we have hydrochloric, the reaction would be faster. Faster means as soon as I add the calcium carbonate, you start having bubbles of gas even before you close the bung. But the ethanoic acid is a weaker acid, so the reaction is not too fast. Less gas escapes before the bung is replaced. A student suggested that the mass of calcium carbonate could be measured by weighing the weighing bottle empty and then weighing it again when containing the solid. So I want the mass of the solid. Should I weigh the weighing bottle and its contents accurately and then reweigh the weighing bottle at the end after I have poured the solid? That's what the experiment did. Or should I just weigh the weighing bottle empty, put in the solid, weigh it with the solid and subtract the two masses? Actually, the way he did it is more accurate, because if we weigh the empty weighing bottle, put the solid and then pour it in, weigh it and then pour it into the boiling tube, some solid may remain inside the weighing bottle. So how am I sure that all the solid is poured into the boiling tube? But if I do what the experiment is talking about, weigh the weighing bottle and its contents, and then pour it into the boiling tube and reweigh the weighing bottle, that is more accurate because it takes into account the traces of calcium carbonate left in the bottle that did not react. So weighing the bottle plus calcium carbonate and then pouring the calcium carbonate into the boiling tube and reweighing the supposedly empty bottle, that would take into account any solid that did not actually go into the boiling tube. So that is much better. Then we have the results of the experiments in a table, mass of calcium carbonate versus volume of carbon dioxide produced, and then we need to draw a graph. Again, to draw a graph, the first thing we do is label the axes. So the mass is on the x-axis, the volume of gas produced is on the y-axis. We distribute the numbers equally so that we use as much of the graph paper as possible. Plot the points with small x's. Join with, in this case, it is a straight line going through the origin, and there is a point away from the line which is anomalous, so we do not include it. We draw the line ignoring that anomalous result. So this is the graph that we should have. Use the graph to determine the volume of carbon dioxide formed when 0.25 grams of calcium carbonate is used. So we look at the graph, we see where is the mass, 0.25 grams. We draw a line up to the graph and then a horizontal line to see the volume. From this, it is 53 centimeter cubed of gas. So when the mass was 0.25, it gave 53 centimeter cubed. Now calculate a value for the molar volume of carbon dioxide using your volume and the equation for the reaction. So this was the equation, and the volume was 53 centimeter cubed when the mass is 0.25 grams. What are we supposed to do? So when we use 0.25 grams of calcium carbonate, it gave 53 centimeter cubed of gas. Now we need to do what? We need to get, first of all, molecular mass of calcium carbonate. Okay, that's the molecular mass of calcium carbonate. Number of moles of calcium carbonate. This is the number of moles of calcium carbonate. From the equation, we relate that to number of moles of carbon dioxide. From the equation, 1 mole of calcium carbonate gives 1 mole of CO2. So this number of moles is the same number of moles of CO2. So now we have number of moles and we have the volume of the gas. Then I can determine the volume of 1 mole. Remember, we're trying to get the volume of 1 mole. The equation is usually number of moles is volume over 24, but it is the 24 that we're trying to get. We don't have 24. What do we have? Volume of 1 mole is the volume that we have in decimeter cubed. So we divided the 53 by 1000 over the number of moles. So that gave me the molar volume is 21.22. So this depends on the volume that we got from the graph. Give 2 reasons why the molar volume obtained by this method is lower than the data booklet value. So what are we doing in the experiment? We're putting a certain mass of calcium carbonate and then close the bung and then collect the gas over water. So first of all, why are our results lower than what it should be? Well, some of the gas escaped before replacing the bung. So the volume of gas that we collect is not the correct volume. Besides, we're talking about carbon dioxide gas, and actually carbon dioxide gas is soluble in water, so it shouldn't be collected over water. So this would be one of the sources of error. Question 3 says, cyclohexene may be prepared from cyclohexanol using 85% phosphoric acid. A simplified procedure is shown. Accurately weigh about 4 grams of cyclohexanol into a pear-shaped flask. Add about 0.5 centimeter cubed of phosphoric acid, few anti-bombing granules. Set up the apparatus for fractional distillation. How do we do fractional distillation? So we put the cyclohexanol into the pear-shaped flask. We put phosphoric acid, anti-bumping granules, and we set up the apparatus for fractional distillation. Heat the flask, collect the distillate that contains impure cyclohexene and water. So what we're going to collect from this is a mixture of cyclohexene and water. Separate the impure cyclohexene and water using a separating funnel. Add a few granules of anhydrous calcium chloride to the impure cyclohexene. Allow the mixture to stand. Decant the impure cyclohexene into a clean pear-shaped flask. Distill the cyclohexene. Weigh the distillate. This is the data that is given. So we're given the molar mass of each of them, the boiling point of each of them, and the density of each. Now, what is the question? First question is, bottles of cyclohexanol and cyclohexene have the hazard labels shown. Again, please learn the hazard labels. So that first hazard label for cyclohexanol, what does it mean? If we look at the list of hazard labels, this means that it is flammable. What about the one for cyclohexene? Well, that hazard label indicates that it is an environmental hazard or it's harmful to the environment. For each compound, state one way in which the risk due to the hazard shown could be reduced when carrying out this preparation. So, they were saying the cyclohexanol is flammable. So how do we reduce this risk? Well, we either heat the cyclohexanol in a hot water bath or using an electric heater. What about cyclohexene? Cyclohexene, we said, is harmful to the environment. That means I shouldn't throw away the wastes into the sink, or we should pour it into a specific bottle in order to dispose of the waste. So these are the methods of reducing the risk. State how anti-bumping granules make liquids boil more smoothly. Whenever we're heating a liquid, we should have what we call anti-bumping granules. These are actually just small balls made of glass. We call them anti-bumping granules because they distribute the heat, so they prevent formation of large bubbles, so that when the liquid starts to boil, it doesn't suddenly burst out of the container. The diagram shows the apparatus used for fractional distillation. Suggests two reasons why fractional distillation is used rather than simple distillation. We're trying to separate what? We're trying to separate the cyclohexene and the water, so we have more efficient separation of the cyclohexene and the water. Draw a diagram of the separating funnel and its contents. You remember the separating funnel is used to separate two liquids that are not miscible with each other. So if I have an organic layer like cyclohexene and water, first of all, we need to look at the density to see which one is above which the other. So what is the density of cyclohexene? It's 0.81. What about water? You should know that the density of water is 1. So cyclohexene has lower density. So in the separating funnel, the cyclohexene layer floats on top of the water. So this is the separating funnel, and we use it to separate organic from water, organic layers from water, because they are not miscible. They will form two layers. The one that is formed on top is the one that has lower density. Explain the change in appearance of the liquid when it is allowed to stand with anhydrous calcium chloride. First of all, what is anhydrous calcium chloride doing? You should know that anhydrous calcium chloride is a dehydrating agent. It's something that absorbs water from the liquid. So the liquid originally is the one on the left. When it has water in it, it is cloudy. But if the solid anhydrous calcium chloride absorbs water from the liquid, then the liquid becomes clear. So the appearance of the liquid, I don't care about the appearance of the solid itself, of the anhydrous calcium chloride. The anhydrous calcium chloride actually will clump up and become a big piece of solid. But we're asking for the appearance of the liquid. Now, the liquid that originally had water is cloudy. When I add anhydrous calcium chloride, it absorbs the water so that the cloudy solution becomes clear. State a suitable temperature range for collecting the distillate in step 7. What are we collecting? We're collecting cyclohexene. Well, cyclohexene has a boiling temperature of what? It has a boiling temperature of 83. So what temperature range should I collect this fraction in? So if it's boiling at 83, then I should collect it within that range. So let's say within 81 to 85, what is coming out is cyclohexene. In this preparation, 3.96 grams of cyclohexanol reacted to form 2.09 grams of cyclohexene. Calculate the percentage yield. Now, in order to calculate the percentage yield, I should first calculate the theoretical yield. So if we start with 3.96 grams of cyclohexanol, how much cyclohexene should we get? From the equation, we said if I have 3.96 grams of cyclohexanol and we have the molecular mass of cyclohexanol already in the table, so I can calculate the number of moles that we're starting with. Number of moles of the cyclohexanol is mass over molecular mass. This gives me the number of moles. Now, looking at the equation, we can tell that the number of moles of the cyclohexanol is the same as the number of moles of cyclohexene. So, we have now number of moles of cyclohexene. We can get the mass of the cyclohexene. Mass is number of moles times mR, which is already given in the table. So, that means that if I start with 3.96 grams of cyclohexanol, we should get 3.247 grams. But what did he actually get? He got 2.09. So the percent yield is what was actually obtained over the theoretical yield that we calculated times 100. This means he got only 64.4% yield. Separate samples of cyclohexanol and cyclohexene product were tested with phosphorus chloride and bromine water. So we're going to add phosphorus pentachloride to cyclohexanol and cyclohexene. The first question is, phosphorus pentachloride is a test for what? We should know it's a test for OH. And this could be an OH of an alcohol or an OH in an acid. So if we react the phosphorus pentachloride, it should give HCl fumes, which are misty white fumes. So cyclohexanol has an OH. It's an alcohol. So it would give steamy white fumes. What about cyclohexene? Cyclohexene is an alkene. Alkenes do not react with phosphorus pentachloride, so there will be no change. What if we add bromine water? Again, bromine water is test for what? You should know bromine water is test for alkenes. So with alkenes, the bromine water turns colorless. So the orange solution of the bromine water turns colorless. But with the cyclohexanol, there is no reaction. So the orange solution remains orange, or the color does not change. But with an alkene, the color of the bromine water is removed, so it turns colorless. Question 4. A student is required to determine the concentration of hydrochloric acid using a solution of sodium carbonate of this concentration. Fill a clean burette with hydrochloric acid. Pipette 25 centimeter cubed of sodium carbonate into a conical flask. Add a few drops of methyl orange indicator. So in the flask we have sodium carbonate and methyl orange, and in the burette we have dilute HCl. Carry out a rough titration. Do you understand the meaning of a rough titration? That means the first titration that we do in which we have no idea what the result should be, so we call it a rough titration. Carry out accurate titration. So once I've done it once and I have an idea how many centimeter cubes of HCl I should use, then I can carry out accurate titrations until we have concordant results. And remember that concordant results are results that are within about 0.2 centimeter cubed of each other. So there are results that are very close to each other. State the color change of the indicator at the end point. Now, if I put methyl orange on sodium carbonate, do you remember the colors of methyl orange? You should know that the colors of methyl orange, in a base, it's yellow. In an acid, it is red, or we can call it pink. When it is neutral, it is orange. So we're starting with what? We're not starting with methyl orange in acid. We're starting with methyl orange in sodium carbonate. So I'm starting with it yellow, and we're going to add until the end point. At the end point, it should be neutral. So the color of the methyl orange should change from yellow to orange. The diagram shows the burette at the end point of the rough titration. Give the burette reading. So when we read this, how can you read it? This is obviously 23 point something. We look at the bottom of the meniscus. So this is 23.4. But since there is an option that it could be 23.45, then it should be in 2 decimal places. So actually this is 23.40 as opposed to 23.45 or something else. The student refilled the burette, prepared a second conical flask by adding sodium carbonate and methyl orange. Describe how an accurate titration should then be carried out. So what are we trying to describe? We've done the experiment and we found that the volume should be around 23.4. But we think that this actually is not very accurate. So I need to repeat the titration. But when we repeat the titration, what we do is we add, I know it should be around 23. So I add about 20 quickly from the burette. And then I know that now I am near the end point. So I start adding drop by drop with swirling until the solution just turns orange. Then usually that would be more accurate. The mean titer from 2 accurate titrations was 22.65. So that is the volume of HCl. Calculate the concentration of HCl. Now what do we have? We have the sodium carbonate has this concentration. And we put 25 centimeter cubed of the sodium carbonate in the flask. So we're starting with number of moles of sodium carbonate, concentration times volume. This is the number of moles of sodium carbonate. And remember, the volume has to be divided by 1,000 in order to change it to decimeter cubed. Then the next step is look at the equation. What are we trying to determine? We're trying to determine the HCl. So the equation says 1 mole of sodium carbonate reacts with 2 moles of HCl. That means the number of moles of HCl have to be twice the sodium carbonate. So if I have this number of moles, then the number of moles of HCl is twice of that. So that's number of moles of HCl. And we're asking for concentration. How do we get concentration? Concentration is number of moles over volume. So the number of moles that we got over the volume that he gives. He says the mean titer from 2 accurate titrations was 22.65 centimeter cubed. Divide that by 1,000, put it into the equation, and we find that the concentration of HCl should be this. Do we understand all of? So this is the end of the paper. I hope this was useful to you. Please study anything that you were not able to answer, and thank you for listening.